Okay, hello class, and welcome to 6.1 Newtonian gravitation. Now, this is the start of a new unit, Unit 3, Gravitational, Electric, and Magnetic Fields. So we're talking all about different force fields. And Chapter 6 is just about gravity. Now, it's actually a really short chapter. We're just going to have 6.1 and 6.2, and some of it might even be reviewed, depending on what you saw in grade 11. To start off, we're talking about the universal law of gravitation. And that tells us that any, I'm underlining any two objects experience a gravitational attraction related to their mass and distance. So it doesn't matter, gravity isn't just for the Earth. Any two objects will experience gravity between them. And we have an equation for that. Our equation is Fg equals big G m1 m2 over r squared. Okay, this is the force due to gravity. It's just like what you saw with mg, the little g before, but now we have something a bit more general. And we're using this big G, which is called the gravitational constant, and it is equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And this is our big gravity equation that will work for any two objects. You'll notice that Fg is related to 1 over r squared. This is called the inverse square law. There's lots of things in physics that are related this way. So you notice that as distance, r, becomes larger, gravity becomes smaller very quickly. It becomes smaller with r squared. And that's the same relationship as sound. Sound has that same sort of drop-off. It's the inverse square law, and this is when one value decreases with the square of another value. And so you see this a lot in physics. Here we'll just say Fg is proportional to 1 over r squared. This is the inverse square law. Okay, so we have an equation. Now it's just a matter of applying this thing. The first problem says the centers of two uniformly dense spheres are separated by 50 centimeters. Each sphere has a mass of 2 kilograms. We want to calculate the magnitude of the gravitational force between these two spheres. We use our equation Fg is equal to G m1 m2 over r squared, and we can plug in our numbers. We have 6.67 times 10 to the negative 11 times the first mass, 2 kilograms, second mass, 2 kilograms. Divide this all by their distance, which is 50 centimeters or half of a meter. We square it. And that number comes out to 1.07 times 10 to the negative 9 newtons. You can see that's a very small value. So part B says, how much of an effect will this force have on the spheres? Well, I'm just going to say, not much. Because it's such a small force. It does nearly nothing. And that makes sense. If you have two objects, 2 kilograms each, separated by half a meter, you know that they're not really pulling each other very, very strongly. If you have those in real life, you don't notice them pulling each other. They are, but it's by a very, very small amount. All right, but now we're going to look at something on a much larger scale, much larger numbers. We're looking at a planet now. It says Eris is a dwarf planet, and it's the 9th most massive body orbiting the Sun. It is more massive than Pluto and 3 times farther away from the Sun. This is real. This is an actual planet in our solar system, a dwarf planet that is more massive than Pluto is, but it's also further away. Eris has a radius of approximately 1,200 kilometers. Part A says an astronaut stands on Eris and drops a rock from a height of 0.3 meters. It takes 0.87 seconds to reach the surface, and we want to calculate the value of g on Eris. Well, let's see. We're going to use kinematics here. Our delta d is 0.3 meters. What else? Delta t is 0.87 seconds. The initial speed is 0. And we want to figure out g. And I'm just going to use g in my equation for acceleration. G is the acceleration due to gravity here. So I can use an equation. Delta d is vi delta t plus 1/2 g delta t squared. Again, I'm just using g as my acceleration value here. Okay, great. Now, vi delta t. Vi is 0, so this whole term becomes 0. That means that if I want to find g, I just need to worry about this second term here. So I can rearrange g is equal to 2 delta d over delta t squared. And this will give me 2 times 0.3 over 0.87 squared. That gives me a value of 0.7927. 0.7927 meters per second squared, because we're dealing with acceleration here. So that's our value of g. And if we want to use significant digits, we should probably round that off to 0.79 meters per second squared. Good. But in our next calculation, I want to use the more precise value. We want to calculate the mass of Eris. Okay, so we just calculated g, which is the gravitational field strength. And you remember from dealing with gravity on Earth, we often say that Fg is equal to mg. Well, that's still true. We have a different value of g, but it's still true. But we can also say it's equal to this other equation that we have, gm1m2 over r squared. Okay, and we're going to use both of these equations. Now notice on the left here, mg, maybe I'm just going to call this m1g, where m1 is going to be the mass of our object, and m2 is the mass of Eris in this case. Okay, so I want to solve for m2. You'll notice that m1, m1, they cancel out, and I'm ending up with a statement that looks like this. G is equal to gm2 over r squared. And if I rearrange, this gives me m2 is equal to gr squared over big G. And now let's just put in some numbers here. We had g was 0.7927. R, we're told in the problem, r was 1,200 kilometers, which is 1,200 times 1,000 meters. And we divide by g, which was 6.67 times 10 to the negative 11. Now dividing by that really small number, it's going to give us a really big number in the end. So, oh, I forgot to put a squared there on that term, and this all gives us, well, a very big number. Let's see, 1.7 times 10 to the 22 kilograms. That's our mass. And that makes sense. A planet should be very massive. Last piece here, an astronaut stands on Eris and drops a rock from a height of 2.5 meters. We want to see how long it would take the rock to reach the surface. Well, we have delta d is 2.5 meters, and we want to find delta t. We know again that vi is equal to 0, and now we have our acceleration. G is 0.7927, and we're trying to find delta t. We can use the same equation we had before. Vi delta t plus 1/2 g delta t squared. And we can rearrange to solve for delta t. Now remember again, vi delta t goes to 0 because vi is 0. So if I rearrange, I get delta t squared is equal to 2 delta d over g, which means that delta t is the square root of that, 2 delta d over g. So the square root of 2 times 2.5 divided by 0.7927, and this gives us a value of 2.5 seconds. That's how long it would take to fall. So you see, we can just use g like we would on Earth. It just has a different value now. All right, next page here. We have 3 large spherical asteroids arranged in space at the corners of a right triangle ABC. Asteroid A has a mass of 1 times 10 to the 20. Asteroid B has a mass of 2 times 10 to the 20 and is 5 times 10 to the 10 meters away from asteroid A. And we've got some numbers for asteroid C. Determine the net force on asteroid A from asteroids B and C. Well, we just have forces acting on A. So we have a force C. B on A is going to be acting downwards like this, or sorry, opposite. B on A, B is going to be pulling A towards it, so we're going to have a force acting in that direction, and we'll have a force acting in that direction, and we need to figure out what those are. Now, it seems like C is going to give a much larger force, because it's closer and larger. Alright, to do this, we can find Fg is equal to, well, I'm going to talk specifically about the force of B on A. That's equal to G mb ma over rba squared. So this is the distance from B to A. Okay, we plug in our numbers here, 6.67 times 10 to the negative 11 times the mass of B, which was 2 times 10 to the 20. The mass of A was 1 times 10 to the 20, all divided by our distance squared. And so B is 5 times 10 to the 10 away. We square that. And this gives us a number. The force of B on A is equal to 5.336 times 10 to the 8 newtons. Good. Now, I'm going to turn that into a vector, and I know that this is going in the north direction. B is pulling A north. I can do the same thing for the force of C on A. So we've got G mc ma over rca squared. 6.67 times 10 to the negative 11 times, in this case, C has 4 times 10 to the 20. 1 times 10 to the 20, all over our radius here, which is 2.5 times 10 to the 10 squared. This gives us a number. The force of C on A is 4.269 times 10 to the 9. And this is pulling it east. So now I have two forces perpendicular. I can add them at right angles. So we have 5.336 and we have 4.269 times 10 to the 8 here, and this was 4.269 times 10 to the 9. The total here will be our sum of forces, and we'll have some angle theta here. Good. So let's see. The sum of the forces is the square root of 5.336 times 10 to the 8 squared plus 4.269 times 10 to the 9 squared. Take the square root of all of that, and it gives us a net force here of 4.3 times 10 to the 9 newtons. Great. And we need to get our angle. Theta is the tan inverse of, so we want the opposite, 4.269 times 10 to the 9 over 5.336 times 10 to the 8. And this gives us a theta value of 83 degrees. We've got our two pieces here, and so then we can say, therefore, the net force is equal to 4.3 times 10 to the 9 newtons, and we'll say north 83 east. And there's our final answer. Cool. So, let's see. The next one, part B here, determine the net force on asteroid B from asteroid C. Well, if we look at our picture, you can see that the net force on asteroid B from asteroid C, C is going to be pulling it in this direction. So we would do the same process here. We would need to find the distance, this distance here. So that's going to be the square root of RAB squared plus RAC squared. That would give us our distance. And then we have the masses, we have the distance. We would need to get the angle here, theta. And that's all we would need. I'm saying all we would need because I'm not going to take the time right now to solve that problem. The video is already running a bit late. I will leave that for you to give a try. And if you have any questions, of course, just let me know. Okay, so we'll go on to the last page here, gravitational fields. What is a gravitational field? Well, you probably saw this in grade 11 as well, talking about force fields in general. There are lots of different ways to talk about fields, but one thing that we can say is that we can call a gravitational field, we can call them a set of vectors at all points in space that indicate the magnitude, and direction of FG at that point. And so you can imagine that anywhere in the universe, you could put a little point. I could put a point right here. And if I ask myself, what force due to gravity am I experiencing at that point? Well, you would draw an arrow like this, and it indicates what direction it is and how big it is. That's our gravitational field. We have, for every point in the known universe, we can say there is some, we could draw some vector. That's our gravitational field. Okay, and so then along with that we talk about the gravitational field strength, and this is where we say just the magnitude, how strong is it at that point. So this is the force of gravity per kilogram at a point in space. So there are different gravitational field strengths for different locations. Our equation for this is G is equal to Fg over m, which is just the same as saying Fg equals mg. Hopefully you see that. And our units, well, we're talking about g. We've seen it as meters per second squared normally. But when we use it this way, you see we have newtons over kilograms. So we actually say that the units here are newtons per kilogram. It's the same as meters per second squared. I'll write in here meters per second squared. They have the same value. But when we're talking about gravitational field strength, instead of acceleration, we prefer to write it in newtons per kilogram. Because we're saying how many newtons of force does each kilogram receive. Okay, so we'll try using some problems with that right now. It says, assume that Saturn is perfectly spherical with a radius of 6.03 times 10 to the 7 meters and a mass of, it says 0.69. Now I think I've written that down wrong, so give me 1 second here. 5.69. So this should say 5.69 times 10 to the 26 kilograms. Okay. Now we want to calculate the magnitude of the gravitational field strength on the surface of Saturn. That's all we need. We have the mass and the radius. Let's do this. So we can say Fg equals big G m1 m2 over r squared. And it's also equal to mg. Or we can say m1g in this case, if m1 is our object. So again, the m1 cancels out. And if we want to find g, well, we have that equation now. G is equal to g m2, that's just the mass of our planet, over r squared. Okay, so I can plug in some numbers here. We have 6.67 times 10 to the negative 11. The mass is 5.69 times 10 to the 26. And we will divide by the radius squared. So we have 6.03 times 10 to the 7. We'll square this guy. Perfect. That math should come out to giving us 10.438 newtons per kilogram. And if we want to use the right digits here, 10.4 newtons per kilogram. But it's always good to keep this extra one that has more digits, because we'll probably use that in part B. So part B says, determine the ratio of Saturn's gravitational field strength to Earth's gravitational field strength. Well, okay. We know Earth's is 9.8. We have 10.438 here. So we can say G Saturn over G Earth. Well, this is equal to 10.438 over 9.8. This gives us a ratio of 1.1. Notice there's no units here. We have G over G. The units cancel out. Okay, and there we go. So our ratio, we could say that it is 1.1 to 1. That's our ratio if we're talking about the gravity on Saturn compared to the gravity of Earth. So that's Saturn to Earth. Okay, and hopefully you've seen this notation before, using the colon to represent a ratio, a comparison like that. Okay, that's the end of the lesson. It's been a bit of a long one. I hope you enjoyed it. You've got some homework problems at the end. Great. See you in the next one.